Good afternoon. I am SIDDHARTH Sharma from Arya College of Engineering, ITM, from Department of Mechanical Engineering. I am presenting introduction to boundary layer. That is, what do you mean by boundary layer and boundary layer thicknesses. These are the content which I will cover. That is introduction of the boundary layer. Then what is boundary layer thickness? That is denoted by delta. Boundary layer displacement thickness, that is denoted by delta star. Velocity boundary layer, force convection, and hydrodynamic and thermal boundary layers. So, the concept of boundary layer was first introduced by the German engineer Prandtl in 1904. According to Prandtl theory, when a real fluid flow past a stationary solid boundary at large values of Reynolds number, the flow will be divided into two regions. A thin layer adjoining the solid boundary called the boundary layer, where the viscous effects and rotation cannot be neglected. An outer region away. The surface, the object where the viscous effects are very small and can be neglected, the flow behavior is similar to the upstream flow. In this case, a potential flow can be assumed. Since the fluid at the boundaries has zero velocity, there is a slip velocity gradient from the boundary into the flow. This velocity gradient in a real fluid sets up shear force near the boundary that reduces the flow speed to the boundary. The fluid layer, which has had its velocity affected by the boundary shear, is called the boundary layer. For smooth upstream boundaries, the boundary layer starts out a laminar boundary layer. As the laminar boundary layer increases in thickness, it becomes unstable and finally transforms into turbulent boundary layer. When the boundary layer has become turbulent, there is still a very thin layer next to the boundary layer that has similar motion. It is called laminar sublayer. This is the diagrammatically arrangement of the boundary layer, in which we can see the region of laminar boundary layer, then transient region, then the turbulent boundary layer. Overlap layer, buffer layer, we can easily see the velocity lines are shown on the left hand side, and at the x distance we get the laminar boundary layer after the transient and the turbulent. Now the development of boundary layer for flow over a flat plate and the different flow regimes. The vertical scale has been greatly exaggerated and horizontal scale has been shortened. The turbulent boundary layer can be considered to consist of four regions characteristic by distance from a well. The very thin layer next to the wall where viscous effects are dominant is the viscous sublayer. Next to the viscous sublayer, the buffer sublayer in which turbulent effects are becoming significant. Above the buffer layer is overlap layer in which the turbulent effects are much more significant but still not dominant. Above that, it is a turbulent layer in which turbulent effect dominate over viscous effect. Now, what are different type of boundary layer thicknesses? The boundary layer thickness is defined as the vertical distance from a flat plate to a point where the flow velocity reaches 99% of the velocity of the free stream. Another definition of boundary layer are boundary layer displacement thickness and boundary layer momentum thickness, that is given by theta star and delta star and theta respectively. Now boundary layer displacement. This diagram shows the boundary layer displacement thickness. We will discuss. Consider two type of fluid flow past a stationary horizontal plate with velocity u, as we can see in the figure. Since there is no viscosity for the case of ideal fluid, that is figure A uniform velocity profile is developed above a solid wall. However, the velocity gradient is developed in the boundary layer region for the case of real fluid with presence of velocity and no slip as the wall B. The velocity defects through the elemental strip of cross section BB is UU. Then the radiation mass flow rate is obtained as where which B is the plate width, and these equations show the boundary layer displacement thickness. Another definition of boundary layer thickness, the boundary layer the momentum thickness theta is often used to predict the drag force on the object surface. The total momentum reduction is given by integration from 0 to delta rho u minus u b dy. After that, we will get, after this calculation, we will get theta is equal to 0 to delta u by u 1 minus u by u into dy. In continuation of boundary layer thickness, we will discuss this. Theta is known as the boundary layer momentum thickness. The momentum thickness represents the vertical distance that the solid boundary must be displaced upward so that the ideal fluid has the same mass momentum as the real fluid. In this diagram, we can see the velocity boundary layer. This diagram we have seen in the previous slide, and another again we are seeing the displacement boundary layer, the development of the boundary layer for the flow over a flat plate, and the different flow regimes. Now, velocity boundary layer. Velocity boundary layer, the region of flow above the plate bounded by delta, in which the effect of the viscous shearing forces caused by fluid velocity are held. The boundary layer thickness delta is typically defined as the distance y from the surface at which u is equal to 0.99 into v. The hypoline of u is equal to divides the flow over a plate into the region. Now we will discuss the force convection. External flow. An internal flow is surrounded by solid boundaries that can restrict the development of its boundary layer. Momentum balance, inertia forces, pressure gradient, viscous forces, body forces. Energy balance, convective flux, diffractive flux, heat generation, energy storage. Hydrodynamic and thermal boundary layer. As we have seen earlier, the hydrodynamic boundary layer is a region of a fluid flow near a solid surface, where the flow patterns are directly influenced by the viscous drag from the surface wall. The thermal boundary layer is a region of a fluid flow near a solid surface, where the fluid temperatures are directly influenced by heating then cooling from the surface wall. The two boundary layers may be expected to have similar characteristics but do not normally coincide. Liquid metal tends to conduct heat from the wall easily, and temperature changes are observed well outside the dynamic boundary layer. Other materials tend to show velocity changes well outside the thermal boundary layer.